We were told Artemis I was a simple test flight to the moon, but the actual data returned by the Orion capsule tells a terrifying story. It didn't just find craters. The first mission recorded radiation levels that didn't just match the Apollo era, they were almost 5 times higher. It discovered a failing heat shield, while NASA's orbiters mapped a South Pole landing zone that is already being targeted by China. The moon isn't an empty frontier anymore. It's a geopolitical powder keg, and even NASA's own reports suggest we might not survive the landing. NASA was broadcasting lunar video back to Earth using its standard deep space network, but inside Orion an entirely different story was unfolding, one the stream didn't show. To the modern eye, those images proved that the next era of spaceflight could be faster, clearer, and seemingly safer than the missions of the 1960s and 70s. But behind all the spectacle, Orion's onboard sensors were tracking something far more ancient, far more dangerous than any technical failure: radiation. Outside Earth's magnetic shield, there is no room for mistakes. Space agencies and their scientists know that getting radiation wrong can be catastrophic. Every burst from the sun, every cosmic ray from deep space passes through flesh and human bones. Even if the astronauts make it through the blasts, the machines keeping them alive could start to fail, especially when modern spacecraft depend so much on computer technology. The only real way to see how these systems will work in space is to test them on missions. But in space, you don't normally get second chances. Travel through the Van Allen belts means confronting clouds of electrons and protons trapped near the Earth. But beyond that, through the Earth's magnetosphere, and the risk is solar storms. Higher energy particles come into play, potentially lethal cosmic rays moving at light speed that can rip human DNA to shreds. Hollywood shows spacecraft gliding effortlessly through space, not the absolute terror of being blasted by an invisible barrage of particles that can cripple both the mission and the people inside. And if we want to explore space even deeper, longer missions to the moon or trips to Mars, it'll mean throwing astronauts into a world of cosmic chaos. The good news is lessons have been learned. One of the most important of them came from Artemis I's radiation sensors. Scientists discovered that rotating the spacecraft by 90 degrees during passage through the Van Allen belts cut radiation exposure by around half. That first mission was crewed by mannequins. The thousands of sensors in these phantom space dolls, complete with soft tissues and internal organs, revealed that the rotation was like turning a shield to face an incoming aerostorm. So the sensors showed the grim reality of space, but they also showed how there are ways to reduce ever-present danger. The footage looked perfect, but it masked a darker reality: up to 35 millisieverts of radiation on a routine mission. For decades, the deadliest realities of space were hidden in the background, but now we know the truth. The question needs to be asked: how did the astronauts on the Apollo mission survive? Especially at a time when scientists knew much less about space travel and equipment was ancient by today's standards. While the public worried about systems failures or explosions, radiation was always at the top of NASA's concerns. And that was over 50 years ago, when scientists were working with slide rules and primitive computers. Part of the reason the astronauts came back in good health was just good fortune. The Apollo lunar missions flew during what scientists have called a comparatively quiet phase of the solar cycle. Their transit time was also short and that limited radiation exposure. But had a large solar storm erupted while they were outside of Earth's magnetic shield, history might have looked very different. Timing matters. NASA knew it then, but it understands it far better now. The sun moves through cycles of activity, but with modern forecasting technology, we can judge when it might be the safest to leave low Earth orbit. The only problem, NASA's solar and space weather scientists freely admit that they don't know how the strongest, most deadly flares are generated, so they can't predict them. The astronauts of the Apollo era made it look easy, so easy that some of the moon landing doubters of the future would look at the radiation data and refuse to believe men ever went to the moon. During Apollo 17, astronaut dosimeters recorded relatively modest radiation exposure, about 5.5 millisieverts over 12.5 days. That is manageable by spaceflight standards. A chest CT scan can involve several millisieverts. Acute radiation sickness usually requires far higher short-term doses, but Artemis I returned data showing a much higher overall mission dose, about 26 to 35 millisieverts over 25.5 days. The mission was almost twice as long, but the dose was almost 5 times bigger. But Apollo used a few dosimeters. Artemis used a lab full of sensors. Same space, different measuring sticks. It made a difference. Space didn't suddenly become more dangerous. The real lesson is simpler. The longer humans stay beyond Earth's magnetic shield, the higher the dose climbs. But that's when things are going well on shorter missions. A round-trip mission to Mars is estimated to expose astronauts to roughly 1,000 millisieverts, well over NASA's safe career limit. And just one solar particle event, SPE, like a massive solar flare, could deliver 1,000 plus millisieverts in a matter of hours. This is where modern safety mechanisms kick in. Data from the Artemis program shows a far more detailed picture than ever before. Even simple maneuvers, orientation, shielding placement, and belt transit path can drastically change radiation levels during a mission. And modern spaceships come with storm shelters. Astronauts can reconfigure the interior of the spacecraft and sit the storm out in zones where they won't suffer from acute radiation syndrome. It's designed to keep the radiation dose around 35 millisieverts in normal conditions and below 150 millisieverts inside the shelter during a solar event. And if the astronauts are wearing their AstroRad vests, that can help lower the dose. It buys astronauts time, but unfortunately it doesn't change the laws of physics. The danger is always there. If we eventually build bases on the moon, we'll need much more than vests on our bodies. NASA's Space Radiation Analysis Group, or SRAG, has openly discussed contingency plans for future lunar missions. They included devising new kinds of storm shelters for when particle storms start raining down on the ship. But the question is, will they work? It's just a fact of space travel that if something goes wrong, it can go very wrong. You can't completely escape the violence of space weather. And as NASA recently discovered, you never know when something you have tested on Earth will work in flight. Take, for example, the Orion's heat shield. Entering the Earth's atmosphere at speeds of up to 25,000 miles per hour, the air in front of the spacecraft is violently compressed. This creates friction and heat that can reach 5,000 degrees Fahrenheit. Without shielding, the spacecraft would be exposed to extreme conditions that could lead to catastrophic failure and a loss of the cabin. It's a major component in survival. So, after the Artemis I mission, NASA auditors revealed that there had been critical issues. Critical as in potentially deadly if they weren't fixed for future missions. The public remained blissfully unaware that NASA had run into a very serious problem. The current shield on the Orion uses Avcoat, a sacrificial material designed to burn away in a controlled fashion. Every flight means another cycle of maintenance. A single overlooked fault can turn into a deadly failure. That's what NASA warned in its OIG report IG-24-011. Engineers found after Orion re-entered the Earth's atmosphere in the Artemis I mission, the shield materials had been chipped away in at least 100 spots. It did its job, but the Avcoat hadn't behaved how NASA had predicted. Parts of the char layer cracked and broke off in fragments, leaving a trail of debris. The report said it could, quote, pose significant risks to the safety of the crew. And worse, the debris could potentially damage the parachute needed for landing. NASA used a never-before-tested re-entry technique called the skip entry. Rather than diving straight down through the atmosphere, the spacecraft bounced off it using an aerodynamic lift to skip back out. It came down a second time, but at a slower speed where it could accurately target the landing zone in the Pacific. On paper, it should be a much more precise landing, requiring fewer resources to get the crew out of the water. And because there are 2 events rather than 1, it lowers the acceleration. So the slower landing isn't just more accurate, it's safer. The only issue, it didn't quite go as planned. The Avcoat couldn't take the extra bounce. The heat shield heated, cooled, and then heated again. The internal pressure built up, which resulted in cracking. The agency said that the cabin temperature data was well within limits at around the mid-70s Fahrenheit. But was NASA hiding a grisly truth? If NASA was playing this down, there was every chance that we could have had another Challenger disaster. An independent review agreed with NASA's findings. It was a massive relief, but it didn't erase the truth. One of Orion's most critical safety systems behaved in an unexpected way. This is exactly the kind of engineering surprise NASA fears the most. Re-entry is unforgiving. Once the capsule hits the atmosphere at lunar return speed, there is no safe abort, no second chance. So this time the danger wasn't galactic radiation threats, it was a standard human error. And humans are also the reason why the moon and its natural resources are about to cause a very different kind of explosion, a geopolitical one. Space travel used to be a competition between two political forces, the USA and the Soviet Union. But today, the new battle isn't about walking on the moon, it's about colonization. And this time, the Soviets aren't America's rivals, it's China. The moon has been called a treasure trove of resources, and both nations want to get there first and secure those treasures. China's been sending up lunar orbiters, landers, and rovers off its own back, an expensive undertaking. Meanwhile, the US is leveraging private sector innovation through companies such as SpaceX. And with an international coalition of around 60 different nations to help, it has plenty of backup. So the US has the money and the resources and the friends. China has the will and the determination, and one government which makes all the decisions. That last part matters. One set of rules can mean things get done faster. But it's not that the US and China want to colonize the whole of the moon. They're focused only on one part, a handful of places near the South Pole where sunlight, terrain, and possible access to water ice might just make it possible to build manned moon bases in the near future. It's believed that is where all the water is. And water will be needed to start a colony. What NASA calls the permanently shadowed regions, or PSRs, should be ideal for resource utilization. It's also where they'll find the energy needed to power the bases. But it's not just the lunar South Pole where they'll want to set up shop. It is a specific area around what's called the Shackleton Crater, an area about 13 miles across. It's believed the higher levels of hydrogen in the crater, already recorded, mean that that is where all the ice is. But exactly what's down there will need to be determined. That is the point of building the bases. With a depth of about 2.6 miles, it's still a mystery to be solved, but with almost constant sunlight at some parts of the crater's rim, it might be possible to build solar panel facilities. This is the last frontier of modern exploration, and the Artemis program is determined to build the first lunar outpost at the Shackleton Crater. But China's Chang'e 7 project has also chosen the crater as an outpost site. Both countries are already identifying areas of interest for future extravehicular activities. But if spaceflight itself is dangerous, exploring Shackleton Crater brings a new set of deadly hazards. Parts of the rim are steep slopes bathed in sunlight, while just beyond them lie plunging descents into darkness that might not have felt sunshine for millions of years. Building any kind of station there would be treacherous and expensive. A U.S. study looking at landing sites identified a 1.2-mile radius exploration zone as a perfect candidate, reported as the best peak near Shackleton. It is a tiny piece of land, and China wants it too. It hasn't announced the exact location it's intending to set up a base, but there is little doubt it's the same place where the U.S. will start building. So when things get going, can the U.S. and China peacefully coexist? Experts are already saying that whichever side gets their base up and running first will determine the next century of order in space. A NASA watchdog reports that NASA may now make the lunar landing sometime in 2028 under Artemis IV or V. In 2026, the US said within a decade it'll establish the first permanently inhabited base outside Earth. It has set aside $20 billion to achieve it. China has reported that it will be, quote, sending humans to the moon by 2030. Sanctions haven't slowed China down at all. Chang'e 4 landed on the far side of the moon in 2019, the first ever mission to the far side. In 2024, it became the first country in history to bring samples back from the far side. And now China intends to collaborate with the experienced Russians to build the Lunar Research Station, or ILRS. Construction will start in 2028, with another 11 countries on board. The US and China haven't yet gotten into a war of words over their lunar ambitions, but NASA admitted that China is a geopolitical competitor challenging US leadership in the space domain. Not a year passes without evidence of this competition. In 2011, the US barred China from the International Space Station. 10 years later, Beijing launched its own floating laboratory, the Tiangong, or Heavenly Palace, and a year later it was operational with rotating crews. China's message was clear: we will get there first. Jared Isaacman, the administrator of the U.S. Space Agency, says he won't let that happen. He had China in mind when he said, "We're going to do everything necessary to get back to the moon and never let anyone else take it over again." While both nations are looking to set up a base in the same area, they're also planning to utilize as much of the moon as possible. That includes under the surface. Researchers recently said there could be a giant underground complex of caves that could be transformed into a base. About 150 meters below the surface, there's an area 262 feet long and 45 meters wide, about the size of 14 tennis courts. Believed to be an empty lava tube, the cave could be an ideal place for humans to take shelter against the incredibly harsh lunar environment. If astronauts can get inside, they could study the rocks to better understand the moon's formation. Better still, there might be water down there that could give the US an advantage in its efforts to colonize. At least 200 such cave complexes have been recorded on the moon, and any one of them could provide a base if it's structurally sound. But it won't be easy. The slopes are full of debris. One wrong step could mean setting off an avalanche on the people below. Scaling down over 330 feet and getting back out will also pose a significant problem. But nowhere is more intriguing than the region around the South Pole Aitken Basin. Close to the resource-rich southern polar zone, it is the largest crater on the moon, covering 1,600 miles in diameter and nearly 4 to 5 miles deep. China landed a spacecraft there in 2019 when the Chang'e 4 mission touched down inside the basin. But the United States made a different discovery when NASA's Grail mission detected a huge buried mass beneath the basin estimated to be about 5 times larger than the Hawaii Islands. No one knows what it is. It might be deep mantle material pushed into the surface, or debris from the asteroid that hit the moon 4 billion years ago. Either way, it could be rich in metal, but the moon may have other secrets. There are other lava tubes vast enough to shelter entire neighborhoods. In Marius Hills, estimates suggest tunnels stretching for tens of miles with volumes large enough to rival parts of Manhattan. And that changes everything. Because to engineers, these aren't just space caves, they are the foundations of underground cities. There's space for industry, farming, labs, and eventually settlements. They might be the answer to living on the moon, the ultimate safe place, or at least one of the safest known natural shelter options. Claiming these caves would be a turning point in world history. But there is one major obstacle that stands in the way, and it is tiny: dust. Specifically, lunar dust. Landing on the moon is anything but straightforward. There is no cushion waiting on the lunar surface, no weather, no air, nothing to disperse the exhaust. Just lunar regolith, a layer of jagged glass-like dust created over billions of years. It is these tough edges that give it what scientists have called an electrostatic clinginess. And the worst part, it is notorious for infiltrating machinery. On the Apollo missions, the astronauts complained that it stuck to their suits, scratched their visors, and got into seals. Wherever it went, it attached itself. In 2024, Intuitive Machines' Odysseus became the first U.S. spacecraft to soft land on the moon since Apollo, and when the lunar night fell, it shut down exactly as planned. But tipping over on its side? That definitely wasn't. History had been made, but not in the way NASA hoped. The theory was that Odysseus might have caught one of its legs in a crevice. It might have also been traveling too fast. Dust was not the sole cause, but it reminded everyone that lunar landing margins are very thin. But what happens if something goes wrong while astronauts are transferring between vehicles? The Orion spacecraft isn't just another capsule. It was built for deep space with extra protection and a focus on keeping the crew alive. But SpaceX's human landing system is different. It's designed for mass efficiency, cargo volume, and getting to the lunar surface. One behaves like a heavily protected command capsule, the other is closer to a large transport vehicle optimized for payload. And that difference shows up in the structure itself. Orion's tank-like shielding offers around 50 grams per square centimeter of protection, while Starship's lighter balloon-like skin is closer to 3.2 grams per square centimeter. In radiation terms, thicker material between the crew in space helps, but conditions change when the astronauts move from one vehicle to another. That means the most exposed moments of a lunar mission may not be on the surface, it may be in the in-between moments like docking, crew transfer, and movement through minimally shielded areas. This is what NASA is facing, not just missed schedules, but countless points of failure across every critical layer of the mission. Dust, vehicle transfers, loose panels, anything can go wrong. And it's not just speculation. NASA's own watchdog reports that the Lunar Return campaign is struggling. The U.S. government's Accountability Office, GAO, noted in its 2024 review that the Artemis I was unlikely to land in 2025 as originally planned. And it didn't. The reasons were many, including an aggressive development schedule, major delays to SpaceX's HLS milestones, and ongoing issues with suits designs. The GAO added that if development follows the average timeline of a major NASA project, Artemis III would likely slip to early 2027. The rules for the moon aren't settled, and they might even get messier over time. Right now, countries are working under voluntary agreements called the Artemis Accords. They say missions should respect historic landing sites and avoid getting in each other's way. They also introduced the idea of keep-out zones around active operations. But here's the problem: none of it is clearly defined. What counts as interference? And how big does a zone have to be before it starts blocking other countries from the same lunar terrain? No one agrees on how close you're allowed to get to someone else on the moon. And importantly, Russia and China are not parties in the Artemis Accords. Russia has been critical of them because they represent a US-led framework. China wasn't invited to participate in part because US law bans NASA from working with China. Countries including the United Kingdom, Italy, Australia, Canada, and Japan have all signed the Artemis Accords. But that's not surprising. They're already aligned with the US, and most have their own ambitions for the moon, so they're willing to cooperate to get there. This isn't new. Space has always required international agreements. The 1967 Outer Space Treaty said space should be peaceful and that it should benefit all of humanity. But that is where things get fuzzy. Almost any country can claim what it's doing benefits humanity, even if it mainly benefits itself. A later attempt, the 1979 Moon Agreement, went further. It called for the moon to be used only for peaceful purposes and treating its resources as the common heritage of mankind. But it never really took hold. The US, China, and Russia did not sign it. So where does that leave us? Well, if the US could fix all the flaws in its program and get to the moon first, it could potentially take the high ground and start making the rules. It would be natural, as the US could say it had achieved technological supremacy to benefit everyone. But the US is scrambling. Every mission slip-up gives us more time for rivals to develop their own legal architecture and publish competing rules. They would have the high ground. The fact is this: the words used in those past agreements about benefiting all mankind are currently not realistic. Geopolitics does not work that way. The most useful parts of the moon would not be governed on paper. They'll be governed on the surface. Whoever arrives first, stays longest, and builds presence will set the rules others later accept. That's why a geopolitical space conflict might be unavoidable. But first, someone has to build a base, and it won't be easy.